Hello everyone and welcome to this webinar on our use case, the CP factory. My name is Vincent Rofaz. I'm an industrial engineer and I'm a research engineer for the CECOTP, the research center of the Province de Liège. And I'm working with the HEPL on a project called EMEA Digital Twin Academy. So here is our timetable. After a short introduction of the use case, we will review the software environment. We'll see what has been done on our use case and we will end by a little conclusion. And we are here today to talk about digital twin on our use case, and this in the context of the EMEA Digital Twin Academy project. This use case consists of the digitalization of all the stations of the cyber factory at Technifuture. The project is being developed from a partnership between Job@Skills and Technifuture, who are the owner of the CP factory, and between HEPL and CECOTP, which are the school and the research center associated to the Province de Liège. So the CP factory, or Cyber Physical Factory 4.0 at Technifuture, is made up of different machines carrying out an industrial manufacturing process. So we have assembly by robot, drilling, quality control, storage, and so on. The CP factory reflects the new network production method of Industry 4.0, and it offers a modular system to build a smart factory for teaching and research purposes. The CP factory illustrates the practical implementation of a fully connected factory and can be used to represent the entire value chain: assembly line, logistics, production planning and control, MEMS, quality control. The advantages of the CP factory in education are practical and motivation project exercise for groups, training topics relevant to Industry 4.0 such as RFID, NFC, cloud computing and robotics, the use of mobile robotics with AGVs, and introduction to networking reliable machines. The heart of the system is its modularity. This modularity allows great flexibility in combining different modules in different configurations. And so the use of standard interfaces for each application modules allows them to be exchanged in just a few minutes. So we can swap them and the process will be a bit different, but the stations by themselves will still do the same. Now, the CP factory is made of 10 different modules. It consists of a small factory producing smartphones. There are 3 main components: the front cover, the back cover, and the board that can receive up to 2 fuses. And during the process, the product is being transported from station to station on conveyor and on a pallet and the carrier. So here are the base modules, which consist of a conveyor transporting the pallet. We have the simple ones on the left, linear, and some have a bypass lane that we can see on the right. This depends on the application, and the different application will be set on top of those base modules, and at each application there is a stopper that will stop the pallet for the application. So this is the pallet storage. This is an automatic storage and retrieval system, ASRS. It is equipped with a Cartesian robots for automatic storage and retrieval of the pallets, and up to 32 pallets can be stored in this storage. This is the drilling application. It consists of 2 drilling spindles moving in the Z direction as well as in the X direction. This application simulates the drilling process of 2 pairs of drilling holes in the workpiece. This is the robot assembly cell. It is used for mounting of the workpieces using a 6-axis industrial robot. So the robot places the printed circuit boards into the housing and it will insert the fuses. Camera makes sure the workpiece are correctly oriented. This is the camera inspection application. So the camera is used as an intelligent sensor for quality assurance by vision inspection. So this application is the magazine. It's used to feed the back cover on the smartphone. So there is a pair of poles that will isolate the cover from the magazine and release it on the smartphone assembly. This application is the pick by light. it's made for manually set custom back cover. So this application is 8 storage. Each of them is equipped with different LED and sensor. And so the application will light the proper storage to indicate to the worker which part to take. The muscle press application is made for pressing on the back cover to the front cover to finalize the assembly to close the smartphone. And the pressing process is carried out by a proportional pressure control. The force is measured precisely by a load cell. This is the output module. This is equipped with a 2-axis handling system, and it's used to output the smartphones on 2 other slides. The application module workpiece output can be used as a manual workplace for retrieve workpieces, the smartphone, or in our case with a robot, a cobot, a collaborative robot that will automatically pick the smartphone out of the roller slide and store it in a box. This is the palletizing station with a robot. So this station is designed to pick workpieces from carriers and palletize them inside a transport box, or vice versa. So the transport boxes are being fed and removed by an automatic guided vehicle, AGV. So the digital twin developed for the CP factory is a twin product that will be used for virtual commissioning. The virtual commissioning allows faster familiarization with the equipment. It will be possible to save and pre-configure different scenarios for the learners. Simulation will be an essential tool in the production and development phase of future cells, which make it possible to quickly and inexpensively analyze new solutions as well as new methods and processes. The learners will be able to familiarize themselves with the technologies and commission robots, linear axis, and transport system in the simulated production environment, the digital twin, and this without any danger to the people or to the equipment. Just a mouse click is enough to put a pneumatic cylinder or an inductive sensor in a full state during the simulation, and so the new learning situation can be created to train the students in the troubleshooting in the search of faults. So all the learners will be able to use the simulation program. At the same time, the operation character of the simulated installation is guaranteed at all times. The simulation therefore both saves cost and creates identical learning conditions for all the students. And in addition to that, the simulation technique offers an almost unlimited range of application. So with the software used, it will be possible to connect the digital twin to the real world, and for example observe them both working in parallel. So a virtual prototype becomes a digital shadow, and in this way it's possible to monitor the CP factory remotely for troubleshooting, for example. So during this project, several solution softwares have been tried to find out which one suits the best for the application. We had tried Factory.io, Siemens NX Mechatronic Concept Designer, MATLAB Syncscape Multibody, and ROS. The digital twin was developed after reviewing the best software for the application. So to assess the different solution software, in the first step we used our own use case at HEPL. This is a sorting station from Festo. So this station sorts workpiece onto 3 slides. The workpiece are placed onto the beginning of the conveyor belt and they are detected by a light barrier. The workpiece are stopped by a pneumatic stopper in order to determine the characteristics. And the sensor in the detection module detects the workpiece materials and color, black, blue, metallic. And then we have a pneumatic separator that will guide them to the proper slide. And for this purpose, we redesigned the 3D model in a CAD software, as we didn't have those data. We didn't go into too much details and kept the model simple. as it was just developed here to prove our case. So first, Factory.io. This is developed by Real Games, a developer of 3D educational software for schools, colleges, and other organizations. So this is a 3D factory simulation for learning automation technologies. It's designed to be easy to use. It allows us to quickly build a virtual factory using a selection of common industrial parts. Factory.io also includes many scenes inspired by a typical industrial application from beginner to advanced level. So Factory.io includes a library of industrial parts that can be assembled together to build a digital factory. All the physical properties are automatically managed, so each component is interacting with the environment, gravity, collision, and so on. And this as soon as the component is inserted in the project. So there is no need to define manually all those parameters. This is a plus in the case of only using the digital factory to train for programming. However, Factory.io is limited to the parts included in the internal library. So there is no possibility to import any 3D project that has been designed with the CAD software. So, okay, let's see now how it went for sorting station. So, as we were not able to import the CAD model into Factory.io, we had to use the internal library. We were able to reproduce more or less the same sorting station with Factory.io with the same functions. But for example, the library doesn't have the same cylinder workpiece, so we use some generic products from the internal library to be sorted out. We had to replace the color sensors and metal sensor by a vision sensor. This sensor gives us a value depending on the kind of workpiece it is. So in this case, we've been able to realize something similar, but we saw the limitations of Factory.io and its internal library. And at this point, we understood that we wouldn't be able to realize the CP Factory use case with the software. So Factory.io is limited to the parts included in its internal library. There is no possibility to import any 3D project that has been designed with the CAD software, and then it was not possible to simulate our use case as we wanted, and we could only build something similar with the components available in the library. So this is not good for our use case, but however, it's still a good learning tool to learn automation. So now we will review MATLAB and the SimScape multibody tool. So this provides a multibody simulation environment for 3D mechanical systems such as robots, vehicles, suspension, construction equipment. So you can model multibody systems using blocks representing bodies, joints, constraints, force elements, sensors. You can import complete CAD assemblies, including all the mass, inertia, joint, constraint into the model. So in SimScape multibody, it's possible to build solids in the software environment or to import CAD files, only parts or assemblies. But there is no 3D interface to work on the assembly like it would be in a CAD software. This is not meant to be a CAD software. So what we have here is a schema of blocks linked to each other. So the blocks represent the solid bodies and the links between them represent the constraints of the assembly, like the joints, for example. And so in order to build a model, it's necessary to create those blocks and to configure the solids by setting shapes and dimension or importing a CAD file. So as I said, it's possible to add joints between solids. So those joints will bring the degree of freedom necessary to the assembly. And yeah, this schema of blocks, it can look accessible for small application, but it can be challenging to imagine the outcome of what it looks like on a larger assembly. So this was our sorting station. We were able to import the CAT model. We reorganized a little bit the blocks to have structure. So we've seen that we have different blocks regrouping other small blocks. All the lines are the links between the solids. And really in the down level, we could see the blocks. In those blocks, the solids are defined with the joints. This is so we also see some function, or we define the control of an actuator, or we define the set point coming through the input of the PLC, and or we define the sensor limit. For example, by analyzing the position of the joint and comparing it to a fixed value. For this, we also saw the signals we exchanged through the PLC. So this is done through OPC UA. And for this communication, we had to write a MATLAB script to start the OPC server and exchange the data. So here we were not able to simulate the color sensors. So we used manual switches to say, okay, this is a gray color, or okay, this is a red color. And you've seen how the simulation looks like as well. So with SimScape multibody, the problem came when it was time to simulate the forces around the cylinder. We had to use a force contact library, which has only simple volume functions like planes or sphere. So simulate the conveyor, simulate the cylinder on the conveyor was not difficult, but the forces to get the cylinder go to the slides with the separator, for example, it was very tricky. We were able to do it with some tricks, but we understood it will not work for a more complex system as the use case of the CP factory. Defining some sensors was also a challenge. We didn't find a way to detect the colors, for example. This may be possible, but as we already knew at this step, we wouldn't choose this software. We didn't look too much for a solution, and instead we use manual switch to define the color. The simulation also is very slow. There is a lot of computation happening in MATLAB. We played a little bit with some parameters to optimize, but maybe there is more work to do on that to get a better simulation. And the schema of blocks is really difficult to read. Here we organize and it was okay, but it will become really impossible to under this with the assemblies containing hundreds of elements like we would have for the CP factory. So in conclusion, SimScape multibody is a very good tool for mechanical simulation. Force computation is very good, and a lot of data accessible in real time from the simulation. But we could say it's a little bit less suited for virtual commissioning of an automation application. Then we tried Siemens NX Mechatronic Concept Designer. This is part of the Siemens Virtual Commissioning Software Group. So MCD help us to easily build a virtual model of a machine using existing 3D CAD data. And then we apply physics and kinematics properties to the components to validate the machine operations. So this software includes joints, motion, sensors, actuators, collision behavior, and different kinematic and dynamic properties for all the components that you add in the model. So the simulation is physics-based and interactive. So as we said, it's possible to import CAD models. And MCD is part of Siemens NX, which is a CAD software. So we can use CAD models directly developed with Siemens NX, or we can import models developed with other CAD softwares. The environment is also user-friendly, like most of the CAD software nowadays, and it's easy to navigate in the menu and to organize the project. In MCD, the model is not active when it's first added to the project, it's necessary that the user define rigid bodies to the components, and then physics and kinematics can be applied to that body. So once the components are defined at rigid body, they act with the mass, inertia, and they respond to forces like gravity and collisions. So collisions also need to be manually defined by the user. So the object with collision will collide to each others, and we can choose, there is a whole lot of sets of different shapes that can be chosen, like boxes, cylinders, sphere. So this is according to the shape of the body, and even meshes can be defined for complex shapes. So we imported the CAD model in Siemens NX, and we were able to define all the functions we needed with the joints and transport surface. We were able to define object source, simulate different sensors. So the limit switches are easy to create, and we used collision sensors to simulate photoelectric sensors. And we were able to detect the color associated to the workpiece by using collision categories. And the simulation was good and very similar to reality. So as a conclusion, we chose to go with Siemens NX CD, which was the most appropriate software to do this. And in the end, this is not a surprise because this is the purpose of this software. This is done for virtual commissioning. And before to switch to our use case, we will give a little word about ROS. So ROS stands for Robot Operating System. It's a set of software libraries and tools that will help you to build robot application. ROS is everything you need for robotic project, and it's all open source. We had a look at this software because it's open source, and there's also a 3D simulation environment. We will not enter in all the details, but we found out this was more appropriate for robotics project than for automatic stations, like for our use case. Plus the environment is not really user-friendly, so we need to work in common terminals, and that didn't match with our use case, which the CP factory, which is supposed to be a demonstrator, so it should be easy to use and easy to show, which was not the case of this product. So our use case. Before to start describing what we have been doing in the use case, I will just take a slide to review other softwares of the Siemens Virtual Commissioning group. So MCD has already been reviewed. This is a physical and kinematic model. So this allows the simulation of movements, material flow, material handling, collisions. CIMIT is a simulation platform that will simulate the electrical and behavior model. The simulation platform CIMIT enables test of automation application. Like that, we can simulate sensors and actuators, process attributes and properties, temperature, pressures, hydraulic, pneumatic. And then we have PLC sim, which is the automation model, and then this will simulate the PLC program logic and visualization, input and output interface, startup, shutdown of the PLC, fault and error handling, communication simulations. So for use case, unfortunately we didn't have the time to digitalize all the stations. We will not take the time to explain all the reasons here, but here are 5 stations we have digitalized. The pallet storage, the drill station, the camera inspection, the automatic magazine, and the output station. We will review them one by one, except the camera, which is not really interesting in this case. The first station we realized was the drilling station. The first step was to realize the conveyor with the stopper, though this part is the same for every station, except for the ones with the bypass. And to realize the conveyor, we use a transport bent, and for the stopper, we use a sliding joint. The drill application itself was one of the simplest. This only contains pneumatic movement on the X and the Z axis. And then we have the drills. So the pneumatic movement are realized with sliding joints, and the drill rotations were realized with the cylindrical joints. Collision sensors were used to detect the parts, and limit sensors were used to detect the position limits of the axis. Next station was the back cover magazine. So the pneumatic axis for the lifting unit was realized the same way it was for the drill. The more complex part was the back cover dispenser with the 2 layers of poles that open and close to let go one part at a time. There is a mechanical articulation transforming the direction of the actuator. So it's a pneumatic cylinder that goes in the x-axis. So to the right it goes out, and the articulation is between that axis and the power direction, which we see goes in a direction with an angle. And for that we define mechanical cams in MCD to synchronize both the movements of the actuator and the poles. So in this simulation we had also some work around the collision inside the magazine. So the covers in the stock are in contact with each other, but also with the magazine, in which they need to slide down. We're now able to run the simulation with 3 or 4 covers in the magazine, but the computation becomes too important if we increase that number. And the time scales drops, which decrease the reliability of the simulation. So there are still some improvement and optimization to do over that part with different function on NXMCD to be tried. So we then simulate the pallet storage. So the storage contains 32 places where the pallets are stuck with or without front cover. So the picking unit, it's made of 2 servo axes, X and Z axis. There is 1 rotary pneumatic movement to change from one side to the others, and a linear pneumatic movement to reach the position. And finally, we have 1 gripper to pick the pallets. So it's possible to completely emulate the servo-derived behavior with Siemens CIMET software, but we didn't have the time to try this feature, so in our case we simply choose to command those sliding joints by giving a analogic set point from the PLC, and we use position sensors to send back the position to the PLC as an encoder would do. The rotary axis was made of a hinge joint, so there is not much difference compared to the sliding joint. Only difference is that the vector is circular. For the gripper, so there is a specific function in NXMCD for the gripper. So we need to define the fingers and the direction they slide. And this is what we use to set our pallet gripper. Then for the 32 pallets which are in collision with the shelf, there was a lot of computation for that. And to reduce that computation, we used what is called a bond zone. So it was created around the 32 pallets in the stock. And so this bond zone makes the pallet fixed until they are grabbed by the gripper. And we use kind of something similar when the pallet is dropped on the carrier. So they are linked together and the computation of the collision between them stops. So this is an optimization of the computation in the program. And finally, we simulate the output station. So we have a gripper collecting the final product, the smartphone, and the collaborative robot picking the product to store it in the box. So the x-axis is driven by a Festo controller. We had to simulate its behavior in a MCD. For the gripper, we use the same as for the storage station. So we define a gripper with finger, but for the robot, we defined also a gripper, but with a suction cup. And to drive the robot, so we needed to define all the joints of the robot, and then we used inverse kinematics, so we give points to the robots and the software calculates itself the the path. So this is how we did the robot. So now some comments about our experience with Siemens NX. First, the inverse kinematics that we just talked about and which is used to simulate a robot. So we define the different articulation, the joints, and we group them. So with that we can give points to the software and it will calculate the path of the robot tool. We can ask the robot to avoid collisions and so on. But however, we can notice that the path will not be the same than the real robot, because the software behind is different in the Siemens MCD and in the robot controller, and so the computed path is different. The result is good enough for the virtual commissioning of the PLC, but not for the robot itself. And if we want to do a digital shadow, then the solution would be to get the data from each motor of the robot, like the position, and we send that to Siemens NX. So in that case, the robot in Siemens NX would follow the robot in reality. And also the configuration of the inverse kinematic is very time consuming. The computation of the different points of the path requires a lot of resources, and so the definition of those points is really time consuming because the computer is loading a lot. So we also try to assemble different stations together and simulate all the process, but unfortunately this requires a lot of resources and our laptop was not able to produce the required performance for such a simulation. We could observe the timescale dropping and the simulation was then becoming less accurate. And for information, the configuration of the laptop used for the project was quite a good PC with a decent processor, a lot of RAMs and a good graphic card, but this was still not enough, even it was not a simple office computer. Also, for different reasons in the project, we didn't have time to explore the Siemens CIMIT solution. This would have added some value to our simulation model. So MCD shows us the 3D render of the digital twin, but it's not practical to create complex functions inside that software. And CIMIT is used in this case to create the behavior model of the components like servo drive and so on. So this can be a next step for that project. So a good part of the stations has been digitalized. Some will need some improvement optimization regarding computation load, and 2 big stations with robots still needs to be digitalized. Those 2 stations, they will add a lot of work because there are a lot of things to move, and the robots, as we have seen with the inverse kinematics, that requires a lot of time to configure. So it would also be interesting to assemble all the stations together and try to simulate the complete process. But this will require a lot of capacity from a computer, so we really need a supercomputer to do that. And yeah, that's it for conclusion. So in the future, a project is being created regarding 5G on the CP factory to demonstrate that technology. So the idea would be to access remotely to digital shadows of some station. This remote access would be done on 5G, and for that the digital twin created during this project would be reused for that purpose.